our abstract view for timing analysis, and then simulation and model checking. And I will focus on our Rebecca model and the model checking results that we have. And we build a state space graph, and then we also build a tool, wrote the algorithm to do the path finding and find the end-to-end delay. So this is the beginning of the work that we have started, and we want to, of course, continue, and I will tell you about that, how we want to continue it also. So we have this cyber-physical system of systems all around us. One thing that I've been working on is this interoperable medical systems. You have sensors and actuators and medical devices, for example, in a room in the hospital. You can, the patient can be checked, the respiratory rate can be checked and the pulse rate, and if something is wrong, the monitoring application can automatically send a command to the pump infusion to adjust the amount of whatever it's putting in the patient's blood or something. And this can also be connected to the network. And if, for example, there is some system is installed in for an elderly patient somewhere, and then the system can inform the caretakers that something is wrong, and the one who is closer to the patient can come and take care of the patient. The other example is, so these devices are all working in a network. That's where we move from embedded systems to cyber-physical system, and then cyber-physical system of systems. We have that in automotive industry. We have automotive architecture inside the car. We have now this, this is a picture of the centralized architecture of Volvo cars. Actually, this is centralized, but previously it was also, they have some kind of distributed architecture and control inside the car. You have all these ECUs and components talking to each other over network, and we also have all these systems, all these cars talking to each other. So a generic view can be that, here is my mouse. The generic view can be you have systems talking to each other, and each system is receiving events, messages, time events from sensors, sporadic or periodic sensors, and commanding to the actuators, and they're also talking to each other. So I've been working on actor models now for more than 20 years, and we have been modeling the world view as components in the network. So how we look at this is actually these systems or the components, they are both like actors with some thread of execution, and they have buffers for messages or events to then you can take the messages or events and handle those. And also these actors are talking to each other through the network. So, and this is the systems that we are seeing nowadays all over the place. And this is the model I've been working on now for years. And we built tools and techniques for doing analysis over this model. So I'm going to show you how we use our model and tools to solve this schedulability and analysis and finding the end-to-end delays. The software center companies that have similar applications and we can work on their problems. One is Volvo Trucks and Henrik Lohn. We were talking now for some time, but now I can finally, I had the time and the resource to work on his problem. This is the Viper example that he gave us. And this is not system of systems, but we have all these components talking to each other, and they need to know the end-to-end delay. And there are offsets in starting the work, and that can make the problem more complicated. Also, Darko and Hawaii, they're working on holistic task and message scheduling in automotive architecture. We haven't started any work together, but we had a few 2 or 3 meetings and passed information. The main company that we have been working with is Dive, and we worked mainly with Jesper and Tobias. So Dive is global supplier of green, safe and reliable power control solutions for decentralized power generation on land and at sea. It's established in Denmark in 1933. They have more than 550 employees and represented in 5+ key markets in all regions of the world. So they build solutions for control, monitoring, management and protection of distributed energy production. And they offer products which can have single function components and having a dedicated purpose, or multi-purpose products. And it can be done through multiple different functions in the same product, or multiple products cooperating in a solution. So you can see that a system of system concept is coming in. The application domain that we focused on is this multi-line 300, which is deployed in a power production application and are interconnected to manage power production. So the platform, I'm going to show you the abstract view of this, is this multi-line 300 platform. This provides the real-time Linux operating system and the communication interfaces. And one of the important communications for this multi-line 300 is the EtherCAT field bus communication. And this communication is used for data acquisition from all the different I/O modules in this on this platform. So they wanted to identify signal paths and minimum, maximum, and typical propagation timing between inputs and outputs. I will explain this to you through our abstract view, through having some meetings with people at Dive. We came up with this abstract view that we have these two, the ACM components are the input components for the systems, receiving data from the sensors, passing it to the CPU or the processing unit PCM, and the output one is IOM. We also have this EIM module here somewhere, but at some point we realized together with the experts at the company that this is not really, it has no effect on our calculation, so we abstract it away. These are working with a period of 3 milliseconds, and this one too. So one thing that we did, and I don't know if how many of you are there in other companies that have similar applications or use cases. So you can see that after talking, even this EtherCAT communication, it's somehow abstracted away because it's not on the way of any of these components doing their work periodically. So this boils down to this abstract view. We build a simulation just to make it clear and have it, you know, it's nice. I'm not going to show it. I promised Christian to finish quickly. But we showed them that how these sensors are producing data, and there are the times are estimated, but in simulation corner cases may be missed. And we have to run them, of course, for different settings. So we use the language I told you, Rebecca, Reactive Object Language. This is based on Hewitt Actors. This is a kind of agent-based language. So we have concurrent reactive objects there. Java, the syntax is like Java. I will show you our code. And the communication is asynchronous message passing. There is no blocking send. In theory, message queues are unbounded, but here in this example, it's just one entry. So this is irrelevant for this example, but we are going to extend it. So we need all this information. They will come to play. And computation is taking the message from top of the queue and executing it. We have our own web page, and you can see the list of the projects and tools. And now Tobias was going to use the tool himself. So he basically wrote a Rebecca code for the model himself. And this is something that we brag about, that our language is easy to use and understand. It's not a, although our method is a formal method, we do formal verification, but the language is not hard to learn and understand by software engineers and engineers. So that was our main goal in designing Rebecca, to be usable for the engineers. And Tobias was a very good example for us to, yeah, because he learned it himself and wrote the code himself. So how does this work? We have actors, and in actors we have a queue, a message queue. We have message servers or event handlers here. We have our state variables. And then the execution is that while executing a message server, messages are sent to other actors. And of course, when actors are being executed, they take their message from the queue and they execute the corresponding handler. So taking A and then taking B and executing the corresponding handler. That's how it works. So the generic model that we build, so you saw this ACM and IOM and PCM, but then this is the more generic model that we also showed to dive people and as an example. This can serve for other examples like the Viper or the architecture of Volvo cars also. In each actor, we have a run me and a get data handler. So if you zoom in these two components, they have their own period that they are basically calling this run me handler. This is the main cycle in the component. And when they want to send the message to the other component, they call the get data of the other component. So this get data is like putting the data on the input port of the other component. And this is the code. I put it here for you, but I think I will have time to show you Afra a bit quickly. So this is the code for this generic model with component. You can see that we have the environment variables here. So we have the offset for the sensor. We have the period of the sensor here. You can just change it. And you have the period for the two components, 1 and 2, which are here, these two. And then your component 3 is basically the output one, which sends the data to the actuator. Here in the main part, this is what I said, it's object-oriented programming and this Java-like code. You can see the sensor and the components. Here you instantiate them. And in the code for each of these reactive classes, you have the constructor. Here you start in basically initiated. You have the initial value of the variables and also put the first message in the queue of the actor. So this is initiating the actor. After the actor sees this message in its queue, it will start its work. So this offset, this after sensor offset, is basically starting the actor after some offset. You can model it like that. Here you have the same here for component 1. In the constructor you have your offsets, and then you have the run me and get data in all these components, run me and get data. And then the model checker, when you run the model checker, you build a state space. So here you can see that the only actions, the only events that can be handled are this component 2 run me and component 3 run me. The other things have not yet been sent. No other messages there in the queue of any of the actors. So the system can start with this one or this one. You can see all the alternative execution paths here. And when run me of component 2 is being executed, then it sends the get data to component 3. So this one can be then triggered and executed. You go here, and the run me is executed here. You can also go through this path or the other paths. And component 3, which component 1 can only happen after time is passed, this 110, because we have this offset of 110 somewhere here, you see? So component 1 cannot start before that. So the technical details that you see here shows that with the state space, you can all the timing behavior of the system. And this is just zooming in, and this is the whole state space that Afra will generate for you automatically, so you can see what's going on. And this is a dive sample code with the offset. So this is a sample with one type of offset, and we run that and find the end-to-end delay for this sample. And this is the state space that is generated. So if I think I have enough time, I was quick enough, so I can you see Afra now? Can you see the Eclipse tool?
Yes.
Great. So here you can see the code. So it's not as simple as I showed you. So you have the periods, and you can have also the offset of each component starting. So here you have, I comment this out, but I just kept one to make it easy when I run it. But you can see we got these values from Dive also. And you can see that all these components can have their own offsets. And this question mark shows a non-deterministic choice between these three. So the model checker can basically execute all the possible paths and show you different, go through different paths that can happen. And this is where you instantiate them. And as I told you, this is a complete code, but then we commented out EIM because they were not relevant. And this is the simple generic code that I showed you. So if I run the code, let me run it and show you how it will work. So it will, I don't know what are the offsets now, because it depends on the offsets, how it will. Okay, that was good. So here you only get 201 states. You can see the state space here. You got the dot file of it by converting this to dot, and then you can, here you can see TMO3 dots. By graphics, you can see the whole state space and what's going on when you execute this this system. So you have all the data that you want. Okay, and this is where I just put all of this in the slides. But anyway, I'm almost done. So this is then what we did, especially for this project, was writing this Pathfinder algorithm and tool. It took us a while because you can imagine it will we run out of memory and time if we don't have a good algorithm. And these are the paths, example paths that we got. And here you can see that these offsets for starting sensor and component one. I know Henrik was very interested in this, also Jesper and Tobias. It will change the minimum and maximum end-to-end delays. And also the number of paths are much more here because non-determinism is much more, the overlap is more. So this is just the beginning. So what we want to do, we have to work on automation of the process. Some of the, of course, Afra is there now for years and we can use it, but the rest finding this, and Afra is for checking timed properties. So you can check CTL properties and time assertions in Afra, but not end-to-end delays. So this Pathfinder was developed for this project, and the things in between are not yet automated, and it's not a user-friendly tool for engineers yet, but the algorithm is there now. So we have to work on that. Also the scalability, and we already did a lot, but we have to do more, and composition of systems. So we want to put many of these together and see what happens. And of course, what will make it more interesting is all these heterogeneous, for example, network communication protocols that are there. This was just a simple periodic components. Just one of them was not periodic, but the EtherCAT was abstracted away immediately because it was not on the way. And this is the sentence I got from the talk by Miroslav and Jan, distinction between in-car software and infrastructure fades away. This is what we are working on. We submitted a proposal and also a paper, not yet accepted, but these actors have been there now for years, but the network was not transparent. So what we want to also make the network transparent and find out the variability points. And of course, you have to count in the network delay, the priority of different events that are coming in, which actor to schedule, if it is non-deterministic or there is a priority. And for receiving the messages, there can be overwriting, dropping. For taking, there can be FIFO, EDF, pattern matching. If you come to software, all these things will come in. And for us, for cyber-physical systems, it's not only these simple components anymore. We want to have an actor which is handling all these heterogeneous different triggers. So I'm done.